to today's Hi, and welcome to today's covering of Chapter 6, moving things around in 2D using affine maps. So we're going to look at affine maps, coordinate transforms, affine and linear maps, talk about the difference, look at how to do translations, talk a little bit about more general things, mapping triangles to triangles, composing affine maps, and then go back over the vocabulary needs, so what you should know. So what do we mean by a linear map and coordinate transforms? We've been talking about this for a while now. So we want to be able to take a linear map is going to take some vector in one coordinate system, say E1, E2, and map it to some V prime in another coordinate system, say the A1, A2 coordinate system. And as we've seen, we can represent that by a matrix transformation where we're going to have a column vector times the first element of V1 and another column vector times the second element of V, and that's going to give us the two column vectors together, give us the matrix A. So we can view that as a skew box defined by a point P and the vectors A1 and A2. So I want to translate the origin to be at P, and I want to have E1 go to A1 and E2 go to A2. And so as soon as I have to have that translation, we end up with what's called an affine map. I'm going to have P plus A times X minus O. When O is the origin of the second coordinate system, the one we're mapping from, if that happens to be 0, then we'll just get P plus A times X, which is the most common form we'll be looking at it. So as a numeric example, let's say we have an A1, A2 coordinate system defined by A1 is 2, 1, and A2 is minus 2, 4, and P, the point we want to move the origin to, is 2, 2. And I want to figure out where does a point X in the E1, E2 coordinate system go? Well, in that new coordinate system, we're going to take A, 2, 1, minus 2, 4, times X, 2, 1/2, and then add 2, 2, and I'll get that it goes to 5, 6. And if you want to look at it visually, we're going to map from the original coordinate system and want to know in this coordinate system what the point X2 up 1/2 is when we represent it in this coordinate system. Okay, so we want to say if I was here in this coordinate system, where would I be in that coordinate system? So we can geometrically line these up. We want to take this axis, 0, 1, is going to become that axis. Okay, so we can sort of see that this point is twice as far along the line, which is why X prime here is twice as far along this vector. And then A2, we're going to map E1 into A2, but we're only going to go halfway along. So the vector V prime is going to be this vector A1 times the first element of our transformation matrix and A2 times the second, and that'll put us here. So coordinate transforms are about mapping one coordinate space into another, and this affine transformation of multiplying by the matrix and adding the translation gives us an easy way to do that. Okay. Second example, assume we have a different transformation. A1 is 2, 1, but now A2 is 4, 6. And again, we're going to keep P as 2, 2. And I want to figure out what is the point 6, 6 in that coordinate system in the E1, E2. So I can map back to the previous transformation. And now we are going the other direction. So I actually end up with a linear system AU equals R minus P, because we know that R is equal to AU plus P. So we just pull the P from this side to that side. We solve, first we subtract off P from R, so we go from 6, 6 to 4, 4. And now we have to solve for U. AU equals 4, 4. Going back to what we did in Chapter 5, you know how to solve for that kind of system. So then you can get that U is 1/2, 1, 1/2, which you can see that it works fine going back to the previous example. So some nice properties about them. One useful property is that ratios along a line are invariant under linear maps and affine transformation. And as a special case, barycentric coordinates will be preserved. So if you remember, we can think about a parametric representation. I can go from one point to another, from P1 to P3, as I vary T from 0 to 1. And if I let P2 equals that, after an affine map, I can look at what that'll be. It's just X prime after the affine map will be AX plus P. If I put in this representation and I map each of the points, so I'm going to get a 1 minus t times p1 plus t times p3 plus p3 plus p. Collect those and simplify, I get that the result of this is 1 minus t times the quantity ap1 plus p, but ap1 plus p is just p prime, the affine transformation applied to p1, and plus t times ap3 plus p3, but again this is just p prime. So here we're going to get that p2 prime, the position after mapping, is just the same ratio of p1 and p3 put together after mapping. And here we're going to make use of the fact that t1, 1 minus t1 plus t equals 1, which is true. And again, as I said, this is true for any points that we define using barycentric combinations, so we'll have some nice properties of what we want to be able to do with those. So another, and maybe a more, another property, which you can actually see comes from that, but it's also related, it's nice to look at in general, is that affine maps map parallel lines to parallel lines. If I take two things that didn't intersect before they mapped, then they won't intersect after they map. And two lines that intersect before the map will continue to intersect afterwards. So if I take these lines, these are with horizontal and vertical lines that are parallel and a bunch of intersections. After any affine transformation, these lines will be parallel, but now skewed, but they'll still intersect. And the point of intersection is the transformation of the point that was going to be intersected. So now you think about this, like, who cares? What do you want to do with this? Well, there's actually some very practical things you can do, even with just 2D. If I want to think about trying to align a map, I can have a map and I want to put it in some particular coordinate system. I can, given the map's coordinates, I can compute the translations east and north, because the map tells me where north is, and then figure out the rotation. The map tells me scale, I can scale it back down, so this way I can do some very simple operations to align a map to some other map. For example, if I have a building overlay and I want to have that building overlaid on a general map that I've stolen from the internet and got Google Maps, I can overlay stuff and make them all line up. Sometimes the maps don't come with north and all the other information, you just get some drawing. But if you have a drawing, you can go out and measure a couple of lines and directions, then you can use that to figure out where you are, which is standard stuff done in surveying and GIS type systems. You can figure out, for example, a bunch of triangles by citing a bunch of points in the map, figuring out where they go, figuring out the translation you need to move that center, the barycenter to the barycenter, and then a rotation that is necessary. In practice, we'll actually not do this with just one point. We'll end up doing least squares. We'll talk about that later in the semester. But the basic idea of this 2D affine transformation then becomes useful. So now let's go back and look at how we can define all of those transformations. So we use the word translated or translation to mean what we do if an object is moved without changing its orientation. So how is this map covered by a general affine transformation? A pure translation then is just the identity map for the translation plus, for the transformation plus the translation. Translation is an example of a rigid body motion because the object doesn't rotate, it just translates along in space. So very easy to identify them because they don't have any shape transformations going on. More general affine maps will have a general matrix A, and if we think about that, the example with the barycentric, I want to construct an affine map. If I want to rotate a point x by alpha around the point r, because notice we wanted in that example to rotate not around the origin but around the point that was the barycenter in that map, then what we're going to do is first we're going to subtract off the place where we want to translate around. So we're going to translate by r and then do the rotation. So and then we're going to translate it back. So in the end we have x minus r, do a rotation, and then translate it back. So when we get all of that done, we're going to get a times x minus r. This is translating it so that r is the origin. Apply some transformation, in this case a rotation transformation, and then add back r. So this gives us a way of rotating now not around just the origin, which is what a rotation matrix is, but rotating around any point in space. So as an example, if I want to rotate x by alpha degrees around point r, if r is 2, 1, x is 3, 0, and alpha is 90, then I can plug that into the formula. I'm going to take x minus r, so I'm going to get 3, 0 minus 2, 1. It gives me 1 minus 1. I'm going to multiply by my 90-degree rotation matrix, 0, -1, 1, 0, and then add back into 1, and I'll get that that's at 3/2. And if you go graphically, you can say, okay, I want to rotate by 90 degrees around this point to 1. So if I'm at 3, 0, 3 units up from this, I'm now going to be 3 units down from this, and sorry, if I'm 3 units, I'm at 3, 0, so I'm 1 unit up and 1 unit over from here. Then I'm going to end up 1 unit down and 1 unit over, and I'll get that to 3, 2. Sorry, got the direction wrong. It was at 3, 0. I'm going up to 3, 2. So if we want to construct affine maps for other questions, we can just think about what those are and then combine both rotation, reflection, scaling, skew, and translation. So if I let I be some line and x is a point, and I want to reflect x across the line, resulting in x prime, this is, again, an affine transformation. So to do this, what we can do is figure out what's the foot of the point. If you remember, the foot of the point on the line is the point closest to it. Once we have that, we want to find the point on this line, and we know that that's the midpoint of the line between x and x prime. So if we want to reflect, we basically want to go from x to p and then continue on in that direction and go from p to x prime. So x prime is just 2p minus x. And so even though this is, you look at this and say that's not a affine map, well actually it is, right? It's got a p and there's a transformation here, but it's not just a p, it's 2p. So sometimes it's best not to always try and write them as just a translation. This one happens to be the point p was easier to get to instead of 1/2 p. So we can put that together, and it still is an affine map. It's an affine map because it's the form of actually some scalar times a point plus some transformation times the original vector. And that's a more general form of what an affine map would look like. So one of the nice properties that comes out of affine maps is, since we know that any linear combination along this line is going to be mapped to a linear combination along this line, right? We already know that barycentric coordinates or ratios along a line are transformed. Since a triangle is a sequence of 3 lines, we know that given a triangle with vertices A1, A2, A3, there's a triangle T prime with the transformation of those, and that actually turns out to be an affine transformation. Every point inside of it can be written as a barycentric combination of these 3 points, and so once I know where those vertices go, I can map everything else as just this affine transformation. And so how do I find that? Well, given that I want to find an A such that A times x minus A1 plus A prime is going to give me A prime, right? I can find this A to do this. And if I can do that, it's going to turn out that that's going to map all of the triangles. So to find x in T, given any point inside the triangle, I'm just going to figure out A times x minus A1 plus A1 prime. And I could do this with 2 or 3. It wouldn't matter which one I used. But to find A, I'm going to use all 3 of them. I'm going to notice that I can get a vector which is A2 minus A1. I can get a vector which is A3 minus A1. And after transformation, those 2 vectors are going to be mapped to these new points with A prime, A2 prime, and A1 prime, giving us V2 prime and similarly. And then I can combine those back into one matrix so that I know that A times V2, V3 is going to give me V2 prime, V3 prime. We've seen this kind of problem before. Then all we have to do is move A, we have to post multiply by V inverse, and I'll get A is equal to V prime V inverse. So much like solving for how do I map something, that's all we're doing here is mapping the same kind of question. We use this V prime V inverse, where I have the vectors that I started with and the vectors that I want to map them to. And now I've got how to map a triangle. Once I have this, I can apply it to any point in the triangle, and I'll get the affine transformation for any value of x. So turn that into a numeric example. If our triangles are 0, 1, minus 1, minus 1, and 1, minus 1, and I want to map that to 0, 1, so I'm going to leave this first vector alone, but then I'm going to map A2 to 1, 3, and A3 to minus 1, 3. And if you're more visual, I encourage you now to pull out a piece of paper, draw what that looks like so you understand totally what's going on. I'm not going to go through all the math here, but if you take the differences between these, you're going to get Our first matrix is column vectors -1, -2, and then 1, -2. And then after transformation, I'll have 1, 2, -1, 2. I can work through using Cramer's rule or Gaussian elimination, get the inverse of V. So I get -1/2, -1/4, 1/2, 1/4. Post multiply V prime times V1 inverse, and I get -1, 0, 0, -1. Do you recognize this map? Again, if you go back and draw this out, you'll see what this map is doing, and you should be able to talk about what that does. So if I want to continue looking at that, if I have any value of x, now I have that my affine transformation is a, where a is the -1, 0, 0, -1. So I take x minus a1, that translates me to the first corner of the triangle, apply this transformation, and then add back in a1 prime, which in this case was actually the same as a1. So if I had some point, 0, 1/3, and I want to see where that goes, it's going to end up at 0, 7/3. And again, I encourage you to go try that graphically. Now, one of the other nice things about affine maps, and one of the ways we'll use them, is that in fact, affine maps can be applied to a point. And since the effect of applying an affine map to a point is a point, that means I can compose these maps. So if I have some affine map, a times x minus 0 plus p, and if I apply it twice, I'm going to get x prime minus o plus p, which, if you want to expand it, is actually a times x minus o, put that in for x prime, so I'm going to get an a squared x minus ao minus o plus p, right? So if I do that, if p is 0, 0, this actually doesn't cause a translation, and so here I have a map where the color of the points, the lighter they are, the later the transformation. So the first points are black. The first transformation are these darker gray points, and then we get to the lighter gray points, and then very light gray points as this goes on. And here the affine map is a rotation by 45 degrees, and p and a scaling by 1/2. So again, we can define these things in terms of scale and rotation. So I scaled down by 0.5 and I rotated, scaled down and rotated, so you can sort of see how this point moved. And in this case, p was 0. If this, in the second case, all we have done is add the translation of 0.2. So each time I'm moving the center of the circle to the right, and then again applying the rest of the transformation. Now it becomes more interesting when the transformations are more complicated. So here we're going to do something similar, but here we have a skew, 1, 1, 0, 1. So that gives us a skew along the horizontal axis, then a scaling, and then a rotation, in this case by minus 90 degrees, or by 90 degrees. And here's what happens when we apply that with p is 0. So it's going to take this, it's going to skew it, which is going to crush one dimension, and then scale it and then rotate it. So I go from the circle to this first ellipse to the second ellipse, and you keep doing that, and it converges. It goes back down to the last skew puts it back to a circle. But if we have a translation of 2, then every time we do this, we translate it. Now, because the first one was translated and we've changed our skew axes, the second time the translation is not in the x-axis, it's in the transformed x-axis. So it's going to take the first bit of transform, and now it's going to be transformed again, and then again. So you can see that with a very little bit of effort, we now have these complicated shapes being drawn by composing of relatively simple affine maps. This is one map applied, applied, applied. You can compose them and do other things. So here we have simple composition where we take the lower left-hand corner of the letter S, and then we're just going to apply a rotation. And as we keep rotating it a little bit, you get a sequence of S's, and obviously you could do S in any one of these positions. We can be doing that and at the same time scaling them, so you can get some simple shapes by doing a non-uniform scaling and translation. So we're going to apply a rotation matrix, add in a point, and then scale that by a matrix, and we get a sequence of transformations. Okay, so that's an introduction to composing linear maps. This should help you with your first programming assignment where you are going to be doing affine maps. That's what I mean when you're going to read in a matrix that has a scaling matrix or a transformation matrix A and a translation. That's effectively reading an affine map. and then eventually you'll be able to comply a sequence of them. So in terms of preparation, some questions from the back of the book, make sure you've gone through some of these. If we have a matrix A, 1, 2, 2, 1, 2, 1, 1, 2, and a vector P, then I should be able to answer questions like build barycentric coordinates using A as a transformation and show that the barycentric coordinates after transformation are the same. You should be able to use those points, sketch the transformation where T prime is the affine transformation using A and P applied to T, and M prime is the affine transformation using A and P applied to M. Sketch the lines and M prime, and then do this the same. So question is what's this trying to illustrate. Be able to define transformations that will rotate a point around any other given point, define this in matrix form, and that should be, if it's not a rotation, if I want to do something else at that point, you should be able to do it. Be able to reflect points around lines, be able to take triangles, figure out the affine transformation that maps this triangle to that triangle. Given you've done that affine transformation, be able to map points inside the triangle to the other triangles, and think about how that would work in general. And then ask for some basic properties. Affine maps transform parallel lines to parallel lines. Do affine maps transform perpendicular lines to perpendicular lines? Which set of affine maps are rigid body motions? How would you define that? Maybe algebraically. How would you define it in a sort of graphical or more visual sense? And then there's a bunch of terms you need to know from this chapter: affine maps, linear maps, translations, identity matrix, barycentric combinations, invariant ratios, rigid body motion, rotation about a point, reflection about a line, mapping of triangles, and so on. Relatively short chapter, giving you a little bit more time to work in your programming for this week.